Today, we're going to discover how nearshore coastal hydrodynamics and wave behaviour influence the design of shoreline structures. Good morning and welcome to our webinar on designing for wave loads. I'm Georgia Lance, Marketing Officer at Wagners CFT, and I'm here today with guest speakers, Magryn and Associates Technical Director and Senior Engineer Will Souter and Coastal Scientist Freya Barr. Will is the Technical Director at Magryn and Associates and a chartered professional engineer bringing more than a decade of consulting experience in structural engineering, particularly in the coastal and maritime space. Will's role as Technical Director involves assisting with the general running of the business, oversight of technical standards, procedures, and quality assurance. As a team leader and senior engineer, he also manages projects from the initial consultation and design phase through to the construction phase. Freya is a coastal scientist at Magryn and Associates and works in close collaboration with engineers to inform coastal and marine adaptations and infrastructure. Freya brings a keen analytical approach to coastal processes and a science-informed understanding of how these processes interact with our shores and coastal structures. Freya is particularly interested in how wave modelling, sediment transport studies, and hydrodynamic assessments can inform resilient and adaptive design solutions for coastal infrastructure in a changing climate. We are also joined by Wagners CFT General Manager for Australia New Zealand, Ryan Leeson, who will be facilitating the Q&A session at the end of the webinar. Welcome Will, Freya and Ryan. Before we get started, just a few webinar protocols. We are recording today's event and will make the recording public via the Wagners CFT YouTube channel. You can ask a question anytime during the webinar via the chat bubble at the top of the screen. However, we will hold your questions over to the end of the webinar for the Q&A session. And for anyone having difficulties accessing the chat facility, feel free to text your questions to me on the mobile number that I have just popped in the chat now. So let's dive into today's webinar. I will hand over to Will and Freya.
Thank you, Georgia. So today we'll be exploring how waves and coastal processes shape the design of coastal structures. A little bit about us to begin with. So at Magryn, our vision is to help shape more resilient communities and infrastructure for the future by delivering engineering solutions that are future-proof and data-driven, ensuring safety and sustainability are embedded into the designs. Our relationship with Wagners has grown over the years, and we're proud to be a trusted design partner due to our expertise in FRP structures. So our experience designing with FRP has been tested on a variety of projects, in particular in the coastal space, such as jetties, mooring facilities, boardwalks, and beach access structures. So this session today is not just relevant for designers and consultants, also for local government officials, contractors, anyone involved in both the planning and building phases really that wants to get a better understanding on coastal fundamentals. So Freya will introduce the scientific basis for wave behaviour and coastal processes, setting the stage for the engineering design content that will follow. We'll then touch on considerations and some of the standards relevant to wave loads and provide a brief understanding on how waves influence structural design without going too deep into the complexities and the theory. It's quite a large topic. We'll aim to equip you with the general concepts essential to make informed decisions in the planning and design phase. So I'll now hand over to Freya to discuss nearshore hydrodynamics and coastal processes.
Thanks, Will. So to understand nearshore coastal hydrodynamics, it's important to first understand the generation of waves in the open ocean. When waves blow over the ocean for the ocean surface for a long enough period and distance, they generate what is known as sea waves. And when sea waves travel, they disperse and become more uniform in direction and frequency, transforming into swell. For anyone that's familiar with surfing or enjoys spending some time down at the beach, you'd be familiar with what swell looks like, the approaching of successive waves in groupings towards the beach. As the swell propagates towards a coast, the waves transform as the water depth changes from deep to intermediate and shallow water. The transformation process begins when the water depth becomes less than half the wavelength. So that is, the water depth between the top of the wave here becomes less than half the distance between two successive wave crests. The process of wave transformation ends when waves become unstable and break, dissipating their energy on the shoreline or coast. The process of wave transformation includes a decrease in wave velocity, a decrease in wave length as a result of the waves bunching up, and an increase in wave height. Wave transformation happens because the waves are affected by the seabed through processes such as shoaling, refraction, and diffraction. So first I'll discuss the process of shoaling. Shoaling occurs in this section of the nearshore, which I've highlighted with a red circle, where waves feel the bottom or the seafloor and begin to steepen. This causes the first wave in the group to slow down as the bottom of the wave experiences drag along the seafloor. The second wave is moving faster as it is still propagating through deeper water and catches up to the first wave. This results in a concentration of wave energy as the waves bunch up together and the wave height increases. This concentration and subsequent increase in wave height is called shoaling. The way in which a wave breaks at the end of its shoaling process is dependent on wave properties and bed slope. The breaker type can be guided by calculating the Barr parameter. The Barr parameter represents the ratio of the bed slope steepness, shown in the equation here by tan alpha, and the wave steepness calculated from the wave height and the wave length in deep water, which are represented by the H0 and L0 respectively. Based on the result of these calculations, a distinction can be made between three main breaker types occurring on a coastline or a structure. So the first main breaker type is a spilling breaker. These are usually found along flat beaches and begin breaking at a relatively large distance from the shore. They break gradually over a large distance and dissipate practically all of their energy in this process. Plunging breakers are found on moderately sloped beaches and typically have a curling top. When this curling top breaks over the lower part of the wave, a lot of the energy is dissipated into turbulence. Some of this energy is reflected back into the sea, whilst some is transmitted towards the coast, forming a new wave. And the last breaker type here is a surging breaker. These occur on very steep beaches relative to the long swell wave. The wave breaking zone is very narrow, and more than half of the energy is reflected back into deeper water. The waves surge up and down the slope, which is why they're called a surging breaker. Each breaker type can impart different horizontal and vertical wave loads onto structures, so it's important to consider this in the design, as we'll discuss later in the presentation. So the second transformation process is refraction. This phenomenon occurs along a wave crest. When waves approach underwater contours at an angle or obliquely, the sections of the crest that are in deeper water travel faster than sections of the wave crest in shallower water. This results in the wave crest turning towards the underwater contour, and the waves are now approaching from a perpendicular or shore normal angle. And we can see this here in this image of Town Beach at Robe, down here in South Australia, where the waves have an incident approach angle from the northwest. So they're approaching the shoreline obliquely. And as they approach the beach, the changes in bathymetry cause the waves to refract, and they reach the beach at a shore normal angle, as we can see there. The third transformation process is diffraction. This process occurs due to obstructions to wave propagation, such as the presence of a headland or breakwater, or abrupt changes in bathymetry. The obstacles create a large initial variation and transference of wave energy along the wave crest. This makes the wave bend around the obstacle and penetrate into the shadow zone, or the zone on the lee side of the obstacle, as shown in this image here from Pesaro, Italy. The diffracted waves will be concentric and typically 50% to 70% smaller in wave height than the incident waves due to this transference of energy. Though not a wave transformation process, another nearshore coastal hydrodynamic that is important to understand and consider when designing for wave loads is the effect of storm surges. A storm surge is the combined effect of wind setup and lowered atmospheric pressure in a storm center. Wind setup is an increase in the still water level at a coastline due to the wind-induced shear stresses on the upper parts of water layers, which is shown in the diagram on the slide. When wind blows parallel to the ocean surface, it generates a wind-directed current. When this momentum reaches a barrier, such as a coastline, it piles up against the coast, resulting in an increase to the water level, as we can see here. Low atmospheric pressure, such as those that occur in the center of a storm, reduce the atmospheric force pushing down on the water surface, allowing it to rise slightly. This is referred to as the inverted barometer effect. Combined together, wind setup and lowered atmospheric pressure from a storm can have substantial impacts on water levels at coastlines. Particularly relevant in South Australia with the Spencer and St. Vincent Gulfs, offshore storms create storm surges that funnel into the Gulfs and pile up against the coastline. So we can see an example of that on the pictures and the graph on the slide here. On the left are some pictures from Tumby Bay, which is on the east coast of the Eyre Peninsula, and then a graph of the atmospheric pressure in hectopascals measured at Port Lincoln, which is about 50 kilometers south of Tumby Bay. The photos in Tumby Bay were taken on the 25th of May, and as we can see, what occurred at Port Lincoln was quite a dramatic drop in atmospheric pressure. This was the low atmospheric pressure due to a storm surge occurring off the coast, and that water level piled up into the Gulf and piled up against the coastline at Tumby Bay, resulting in very high water levels here. The severity of a storm surge depends on its timing relative to the tidal cycle and the duration of the storm system. Now that I've explained how waves are generated and transformed in the nearshore, I'll move on to how they drive coastal processes and sediment transport. There are two main sediment transportation processes in the nearshore. For simplicity, these processes are split into cross-shore and long-shore transport, but it is important to note that they are coexisting processes. Cross-shore sediment transport refers to the cumulative movement of beach and nearshore sand perpendicular to the shore. This transport is driven by the combined actions of tides, wind, and waves, and the shore perpendicular currents produced by them. Small cross-shore adjustments occur during each tidal cycle, and seasonal cross-shore changes are typical with changes in wave and wind climate. Typically, summer will see more onshore transport or accretion, and winter will see more offshore transport or erosion. Much larger cross-shore events are associated with major storms, such as Tropical Cyclone Alfred, which hit the Queensland coast earlier this year, creating up to 3-meter erosion scarps. This severe beach erosion is thought to be driven by the undertow in the wave-breaking zone with relatively high offshore directed velocities. Longshore or littoral sediment transport refers to the cumulative movement of beach and nearshore sand parallel to the shore. This process is a result of the longshore current that is predominantly driven by waves approaching the shore at an angle. Tides and wind forces can also contribute to this current, but the wave process is the most predominant. The magnitude of longshore transport is directly related to the incident wave energy, as larger waves mobilize more sand, as well as the angle of wave approach. Longshore transport is not as easily discernible as cross-shore transport. Changes to coastlines due to longshore transport are typically recognized due to changes in wave height and approach angle, or the construction of shore perpendicular barriers, such as groins or breakwaters, as shown in these images of the construction of the Cape Jaffa Marina down here in SA. The Cape Jaffa Marina was constructed in 2008, and we can see that there has been a disruption to the longshore transport process, with the western beach here building up quite substantially. Understanding the impacts of climate change on the processes that I've discussed here is imperative in designing coastal structures for long-term resilience, safety, and accessibility. Sea level rise is the most notable threat to coasts, though additional threats include increases in the frequency and magnitude of compounding sea level effects, such as tides and storm surges. The Intergovernmental Panel on Climate Change, or the IPCC, is virtually certain that global mean sea level rise will continue to rise in the 21st century, with increases from 0.5 to 1 meter, depending on the emission scenario. Sea level rise leads to increased water depths, resulting in larger waves breaking closer to the shore. This impacts processes such as sediment transportation, erosion, changes to typical breaker types, and wave loads. Another important predicted impact of climate change to consider in designing coastal structures is the frequency and magnitude of extreme sea level events. The IPCC project that, due to relative sea level rise, extreme sea level events that occurred once per century in 2020 will occur at least annually, so a 1 in 1, at more than half of all tide gauge locations by 2100. Therefore, understanding the influence of extreme sea level events in conjunction with high wave events at specific sites is incredibly important to investigate prior to designing a coastal structure. I'll now pass back to Will to discuss the considerations of designing for wave loads.
Thanks, Freya. So with that foundation on coastal processes and wave dynamics, I'll now talk through how these conditions shape the design of structures such as jetties, ramps, and beach access structures. So let's begin with location. The level of exposure to wave energy at a site can vary dramatically depending on the setting. So for instance, an open coastline exposed to long period swell waves can experience high wave impact forces. In contrast, sheltered bays or behind headlands benefit from reduced exposure. So a good example shown here at Encounter Bay in SA on the Fleurieu Peninsula. The boat ramp was strategically located in the corner of the bay here. The positioning takes advantage of the natural protection provided by the headland. They've also installed a breakwater to further reduce the wave climate. So understanding the wave climate and of the area and how waves interact with structures is crucial for making informed decisions. So I'll just briefly talk about some of the standards and guidelines, such as the guidelines for design of maritime structures, which can help define parameters such as the structure function category, design life, and how that relates to loading scenarios. So they guide to help the selection of appropriate design water levels and wave events based on the annual probability of exceedance. So there's often some engineering judgment required as well when it comes to assessing wave loads based on the acceptable risk, the site exposure, and the intended use of the structure. Now, let's dive into the impact of the different types of waves and the bathymetry on structures, building on what Freya has already talked about. So when designing structures located in the nearshore environment, it's critical to understand that the highest waves do not always coincide with the highest water levels. So as waves propagate into shallow water, they undergo transformation processes, and that can significantly alter the characteristics and the resulting loads. So when waves break onto a structure, this can impart very high impact forces and may exceed those generated under conditions at higher tides, or certain parts of a structure may be subject to higher wave forces depending on the bathymetry of that point in the structure. As such, it's essential to evaluate a range of water levels and wave conditions to identify the critical design scenario. So as you can see here, there's a large difference if you had something like a jetty structure located in this zone where most of the waves are within the wave zone compared to this zone, and you've got higher wave crests in the near shore as they begin to break and the elevation increases. So uplift loads from wave impact can be severe if the crest reaches or overtops the underside of the deck. So this raises a key question. So is it more cost effective to elevate the structure entirely above the wave zone, or to design a more robust structure that can withstand wave forces while partially submerged? If we're elevating the structure, it's important to consider factors such as wave setup, nearshore wave transformation, and potential sea level rise. So if the structure must be located within the wave zone, special attention should be paid to the uplift forces, as mentioned. One strategy would be to incorporate porosity into the decking. So grated systems allow for the pressure to pass through, significantly reducing the uplift compared to solid decking. We've looked at waves on the structure in a cross-section sort of view. It's also important to consider looking at in plan view in respect to wave direction and wavelength. So considering how the waves vary spatially as well as temporally. So waves impacting a jetty from an oblique angle or perpendicular, as shown in the figure here, in that kind of direction, will impose vastly different forces to waves coming from this direction parallel to a jetty. So a wave coming from this direction might cause forces that are acting simultaneously across a large portion of the structure, whereas waves in this direction would run along the jetty and there would only be parts of the structure impacted at one time, such as shown in the photo here. So in regards to specific detailing of structures and how wave loads impact them, the drag coefficient plays a significant role in determining the wave-induced forces. Profiles with higher drag coefficients, such as flat or angular sections, experience much larger forces. So where possible, designers should consider using streamlined profiles, such as circular piles or members with chamfered edges that allow that have lower drag coefficients. Also, consideration where there is wave loads on the structure to minimise the projected area in the critical wave zone. For example, reducing the pile spacing can or may allow you to use lower profile joists or girders to lower the overall force acting on the structure. Now, while understanding wave structure interaction is critical for estimating the loads, it's equally important to consider how the coastline itself evolves over time, over the life of the structure, particularly when you're dealing with dynamic sandy coastlines like we have in a large portion of Australia. They're subject to processes such as storm erosion and long-term recession, as Freya talked about. For instance, a ramp or stairs on a pile that are supported by piles may be structurally sound under current levels, but may in the future become undermined if the beach erodes, as is illustrated here. Similarly, increased water depth due to long-term recession can expose more of a structure to wave action than originally anticipated. This can also amplify the wave loads. To address this in the design phase, it's basically recommended to conduct thorough investigations on the specific site, such as surveying the beach profile modelling where possible, reviewing trends, and this helps us forecast potential changes in the future, allowing us to design structures that can accommodate. So the complexity of wave structure interaction combined with the dynamics of the coast highlight the importance of site-specific design. We'll now look at a few examples that demonstrate different site conditions. These are some beach access stairs in South Australia on the Freya Peninsula. We designed these stairs on a steep erodible beach exposed to powerful Southern Ocean swells. So it demanded a robust and adaptive design. The key features of the design include it was set back landward as far as we could go into the existing dunes to minimise the impact of waves and its exposure during high water events. It also had deep pile footings to resist undermining, and the treads were also embedded well below beach level to allow for that forecasted erosion. We also allowed for uplift loads on the lower part of the structure in the event of wave loads. Another example, at Tumby Bay, we designed a beach access ramp for a dynamic shoreline on the east coast of the Eyre Peninsula, which is the site that Freya mentioned before. It's subject to seasonal profile changes and wave exposure driven by easterly wind events. So the client is after a disability compliant public beach access ramp to replace this existing timber structure that is leaning and has already had issues due to erosion of the changing coastline. The ramp was designed using modular FRP components, allowing for prefabrication, easy transport, and fast on-site assembly. This is just a photo montage, but it just shows what it would look like and how it would interact with future upgrades of the coastal protection measures. So that was a key part of the design, is it had to be adaptable for as they change the coastal protection in the future. It also had pile foundations embedded well below expected erosion depths. And what makes Tumby Bay interesting is highest wave events do not occur during the highest water levels, and that's because it faces east. As you saw in the photo earlier on when Freya was talking about it, when we had the storm surge the other week and a lot of the Adelaide coast was seeing extremely high waves, Tumby Bay was pretty much like a lake because of the direction that it faces. Storm surges are typically driven by southwesterly or westerly winds. So to address this at sites like this, it's important to undertake things like spectral wave modelling to understand the correct load combinations for the design, as well as beach profile modelling to simulate erosion, as I've already talked about. In contrast, the recent storms in SA have seen a number of the historic timber jetties suffering damage due to the extreme water levels and wave conditions. So in many locations, the level of the wave crest exceeded the deck level of the jetties, resulting in extremely high uplift forces and the decks basically popping off as the wave runs along the underside. So for the jetty in the top photo, the failure occurred due to a compromised connection between the headstock and the pile. The lateral wave forces due to an oblique wave angle applied to the structure and result in the crosshead basically disconnecting from the pile completely and the girders and decking collapsing in that section. These recent failures of timber structures serve as a stark reminder of the vulnerabilities inherent in traditional materials, especially in marine environments and under wave loads. So timber's been used and steel has been used a long time in coastal infrastructure, but it's susceptible to corrosion, degradation, and has ongoing challenges. So that's where, in this context, FRP has emerged as a compelling alternative, offering durability, constructability, life cycle benefits in these types of structures along the coast. Coastal environments are complex, and every site has its own unique challenges, as you've seen today. The coastlines are becoming more and more dynamic as a result of climate change, and designing resilient and maintenance-free structures is more important than ever. Thanks for joining us today. We hope you got a bit of an insight into designing structures on the coast. I'll hand back to Georgia now for questions, I believe.
Okay, so thank you very much, Freya and Will, for your presentation. Just before we jump into the Q&A, let me share my screen. I just want to quickly tell everyone about the new Wagners signature series. So, after nearly a quarter of a century in the making, Wagners Composite Fibre Technologies is preparing to launch its signature series, a curated collection of its most trusted fibre-reinforced polymer, bridge and boardwalk designs, all in a convenient kit-style package. With quick turnaround times, zero design and certification costs, and a budget-friendly price point, this series eliminates common barriers to infrastructure development. Each structure is also durable, inert, low maintenance, and lightweight, delivering all the standard benefits of FRP. So if you'd like more information on the signature series, use the QR code on the screen now or reach out via the website. I'll also include the link to the signature series information in today's follow-up email. So I'd now like to welcome Wagner CFT General Manager Ryan Leeson, who will be facilitating the Q&A session of the webinar today. Let's have a look at those questions, Ryan.
Thanks very much, Georgia. I guess we'll start with the technical one first, and it might be, I'm not sure if it's you, Will, or Freya, but can you go into a bit more technical detail on how the wave uplift forces are calculated? And again, the lead on from that is how porosity changes the load. Is it a linear percentage reduction?
Yeah, look, there's a couple of ways you can do it. There's some guidance in the Maritime Structures Code that relates the uplift force to the wave crest elevation and basically the volume of water that's above the deck level. That's a bit of a simplified approach. The other way to do it is to actually do some nonlinear or linear wave analysis and look at the particle velocities along the wave and where it's impacting the structure and what the particle velocity is at that point in both horizontal components and vertical components. And that will give you that's how you can then calculate the force on the structure. And yeah, it's certainly related to porosity, and that would need to be accounted for as well when you're determining the force. You got anything to add to that, Freya? Or?
No, don't think so. Yeah.
Okay, well, I guess a bit of a follow-up from that one, and it's something I've dealt with before in flood loading, but never really on a coastal environment. Is there a consideration for designing in sacrificial components? So, you know, in a high wave environment where you have high uplift and your decking's causing, or your deck of some descriptions causing the issues, rather than designing that out, is there a precedent, or do people often consider designing in sacrificial clips or things like that will fail first, enable therefore the bulk of the structure to remain?
Yeah, that can be done, and yeah, has been done. Like the beach access stairs that we looked at is probably an example of where you could make, because you've only got really potentially the bottom half of the structure might be impacted by wave loads, and you might say that the last lower couple of treads or something might be sacrificial because that they're impacted, or they're getting the potentially highest uplift because of where they're located. But the risk is, and what you've got to be mindful of if you're designing sacrificial components, is you need to make sure that they actually do fail. If you're relying on an item to fail for a design, then yeah, if it's actually more robust or durable than what you're allowed for, then that could cause other problems to the structure. So you just need to be very cautious when doing that, especially when dealing with the unpredictability of wave loads.
Okay. Back to the first two questions that George has sort of posted up there. When you talk, Freya, around predicting storm surges and understanding wave dynamics, can you just run us through the steps that you sort of, when a new project comes along, is it sort of a bathymetric survey? Are they typically available through government bodies for regions, or how do you factor in sort of sediment? Do you forecast sediment movements? Obviously, if you've got a 6-week or 8-week design time from when a project's initiated, you're not going to have the ability to monitor it for a period of time. Is that publicly available government information that you use, or what do you base those models on?
Yeah, so in terms of being able to predict storm surges, that's obviously dependent on the weather, but there are very good resources out there like the CSIRO Canute 3 model, which allows you to pick a point along the coast of Australia and look at the predicted ARI storm surges currently, and also predicted into the future with sea level rise. So that's a really good resource there. In terms of having a quick turnaround and looking at bathymetry or sediment data, there are some areas that are covered under, you can access the intertidal bathymetry. So that's the bathymetry that's within the tidal fluctuations through Geoscience Australia, but this is a little bit patchy in regional areas and it's not fully up to date in some areas. So if there's the ability to undertake an updated bathymetric survey, it is usually quite relevant to. And for sediment modeling or considering those sorts of things, The kind of easy way to do it would be to go out and have a look at the sediment. What's the size? How does that compare? What's the distribution of the particle size? And what's the sand made out of? But to get a fully thorough understanding of how the sediment is moving and how it's predicted to move in the future, then we'd recommend undertaking sediment modelling as well if there's time for it.
Okay, thank you. Question here, FRP is very lightweight compared to timber. Can wave loading induce undesirable vibration into a comparatively lighter FRP structure?
Yeah, good question. It could be an issue. Vibrations, yeah, you'd need to look at the, you potentially, if you're dealing with large spans, it really depends on the amount of deflection and movement in the structure. And you'd need to look at the natural frequency of it and do in your structural analysis to make sure that there's not any adverse effects. But yeah, that's a good question. That's definitely an important consideration because it's a very different material to something like timber. So yeah, you just would need to be very mindful of that and look at that carefully in the design phase.
Yeah, I know on some of our structures before we've done things of intentionally adding dead weight to reduce the vibration potential from be it wind or wave or flood loads. That has probably been a consideration of that. I'm not an expert myself, but that's as I understand. Next question there, can you please elaborate on how varying the spacing between piles affects the wave forces propagated on the structure?
Varying the spacing, yeah. So if you're able to reduce the spacing of your piles, you can potentially get lower profile members, and that may be more beneficial, even though you've got more piles. If you're designing a deck structure that's in the wave impact zone, and if you've got larger joists, that may be a lot more impactful due to those members are typically rectangular and have higher wave forces on them at a higher point where the wave particle velocity is higher at the crest. So yeah, it's just a consideration that if it's not always best just to try and minimize the number of piles and use a larger structure at deck level, because you need to do a bit of trial and error and look at what would be the optimal for the design. So
yeah, we had an example of that recently, I think, from I was briefly involved in Will, where I think we were stuck in a back and forward where to enable the structure to withstand the wave loads, we had to go a heavier duty structure, which increased the cross-sectional area, which therefore increased the wave load. So then you ended up with a heavier structure again, and it was sort of that back and forward. Is that a common occurrence you get to, and how do you often break that deadlock of not being able to balance the two priorities?
Yeah, it's definitely common, and that's part of the challenging. That's part of the challenge of working in the marine environment. Is there's so many variables, there's so many considerations around tides and water levels and different loading scenarios depending on what you're looking at. So it's about taking the time in considering all of those different scenarios and doing the right level of analysis for the type of project or structure that you're working on, that accounts for those complexities. And yeah, in terms of how do you find the right solution? Basically just trial and error. So
be happy to do the iterative process.
Yeah, the iterative process, and it might end up being that just elevating the whole structure above the wave loads is more cost effective and better long term, despite it being might create other challenges in other parts of the project. So
okay, and then as a last question here, I guess it's a learning for a project we had in Queensland recently, where we were factoring in the local council mandated increase in sea level. So this was a pedestrian boardwalk that connected two sort of low-lying coastal areas. Our indication from our coastal modelling put the structure let's call it, it was a replacement of existing timber structure, 1.4 metres above the existing timber structure. For that to occur, the accesses on either side, which is the council car parks and parklands and things, would have been underwater by over a metre for that to have ever actually been used. So how do you sort of go about, or how do people go around that sort of whole of life or whole design piece where you can't just design for a higher water level in isolation if the structure could never be accessed anyway? There's no point having it. Is there a sort of a modular element that people have considered where it could be built into it if the parkland was also raised, or how do they juggle that sort of consideration in projects that you've worked on?
Yeah, exactly. It's about designs being adaptable or adaptive for the changing climate, and we looked at similar issues with Tumby Bay, and we're designing that beach access ramp for how the coastline is currently, and that may not be how it is in 20-30 years, as they've got to adapt the whole coast, and looking at holistically and allowing for sea level rise, they may need to build a rock revetment or elevate the foreshore. So it needs to be designed in a way that it can be modified in the future. And things like modular structures that can be disassembled, disconnected from the piles, or elevated, or rejigged is definitely a benefit in that regard. What are your thoughts, Freya?
I think, as you were saying, following the policies recommendations from state governments in terms of sea level rise and having to build structures higher because of that, that, as Will mentioned, in terms of the standards and guidelines as well, that at some point there needs to be a bit of an understanding or an acceptance under specific events, either high wave events or high water level events, that the structure may be impacted, and that some impacts are just going to have to be accepted. Maybe you decide that a structure, it's okay in this scenario if a structure is impacted by a 1 in 100 event or something like that, but you want to make sure that it's safe and accessible for anything more frequent than that. So that's sort of what did you say before, the engineering
judgment?
The judgment comes into it as well, in terms of also preparing or designing for sea level rise as well.
The sensibility check in the back of it there, which is part of your game. One of the harder parts in your game is how fast it's moving and dynamic it is compared to a concrete structure that's been the same for 50 years. We might have time, I think, Georgia, to squeeze in the last question here. Just a follow-up question, I believe this is to the number of piles. Say for a 4-pile dolphin structure, is there merit in a monopile being used instead of the typical 4-pile dolphin structure? I'm guessing this is around reducing loads. So is there merit in looking at options like that to reduce load?
Yeah, I think there definitely could be merit in that. So without knowing all the specifics, and whether it's got other trade-offs between using a singular monopile compared to, because obviously if you're using a dolphin structure with 3 piles, it may work better if they're connected, may provide a higher stability. So you'd have to weigh that up between the potential reduced wave loads with it being a single pile compared to it just being a singular cantilever structure, whether instead of an integral 3-pile dolphin sort of setup. So, but those are the sorts of things that it's definitely worth looking at and doing in the planning and the concept phase, and that's why it's important to have an understanding of these types of things and wave loads in those earlier stages, because otherwise you can run down a path that may not be optimal. And worst case is that it gets to the point of things being constructed in the wrong location or not accounting for the right things, and it's very hard to go backwards once that's done. So
and no different to geotech, I guess. Often it's important to have those conversations and understanding at concept stage, because it's a long way back once you're down a detailed design piece. So thank you very much for your Q&A today. Georgia, over to you.
Beautiful. That concludes our presentation for today. A big thank you to Will and Freya for their involvement, and thank you, Ryan, for facilitating the Q&A session. If you'd like to share your thoughts on today's webinar, please feel free to complete the feedback form by using the QR code on the screen, or I will also just pop that in the chat now as well. Or perhaps you'd like to be a guest speaker. If that's the case, you could fill out the feedback form and let me know, or feel free to send me a text, give me a call, reach out on LinkedIn. However you want to connect, I would love to hear from you. Coming up in July, we'll be exploring the design and construction of Lili Bridge in Papua New Guinea, focusing on piling, splicing and engineering solutions for remote and challenging environments, with guest speakers Wagners CFT Chief Technical Officer Michael Kemp and Tara Holdings Project Manager Tom Derby. If you're interested in this webinar, just use the QR code on the screen now to register for your free online seat or to receive a recorded copy of the webinar. Link will also be in the follow-up email, and I will pop it in the chat now as well. That concludes our webinar for today. Thanks very much for coming, and we're going to go out on the video of the FRP coastal structures from the beginning of the webinar. Enjoy, and we look forward to seeing you next time.